I've spent quite a bit of time developing the formalism of periodic orbit theory. I switched gear, maybe pedagogically. There is still some painful discussion of group theory that I'm skipping right now, but I'll return to it later. Because I find the goal very intuitive. The question is, how do we compute transport coefficients? So these are the properties of t goes to infinity. And the emphasis is this is a measurable property. You can imagine doing an experiment in some system is a lattice. It could be atomic physics experiment in the labs in the basement here, where you look at lattices, optical lattices, and you move electrons around ions. It could be something in nanophysics like graphene surfaces or some other periodic arrays. There is a velvet revolution that's happened here that most people are not aware of. The theory of transport coefficients is an extremely well-developed subject in statistical mechanics. And it's usually based on Boltzmann kind of assumptions. So Boltzmann assumption is so-called Stoßzahl-Ansatz, but idea that once you have a collision between your molecules or whatever your dynamics is, you can erase your history and just proceed as though this is the only thing that happened, this collision. And that's the basis of Boltzmann theory of fluids. So this theory is amazingly successful. It's very beautiful. But it's very hard to see how the corrections would work in this theory when you actually start putting history in. So it's quite difficult. So if you read Physics Today, last month has an article about people measuring random walks. It's of interest for biophysics in that case. And noticing that they have funny distributions of angles, successive steps. So there is, maybe some other information, and that has to do with the memory of the process. So while random walks look very simple to you, there is lots of important stuff still to be dug out. And the theory that I'm presenting to you is amazing because we are like elephants. We don't forget anything. So there is no assumption that memory can be erased. All the memory is included because periodic orbits are things that capture the memory. They have some time for them to come back. The theory is based on organizing contributions from longer and longer recurrence times. And it's very sweet. What I'll give you today, you can do everything by hand. And I will use periodic orbit theory to tell you how you compute diffusion coefficients in one-dimensional lattice. So this is doable by hand. Now, this model is so simple that in literature there are much smarter things. So Christodoro and Klages, etc. People who have worked on this have smarter ways of computing than what I'll give you. But it's a very nice exercise anyhow. So that's the goal. And the simplest coefficient is to say what happens to x squared times t. So how far you went from wherever you started, and assuming that you start at the origin. And there is a theory of that says there is a diffusion constant of Einstein, which says that this thing grows proportional to the time. And again, this growth proportional to the time is not a big deal. You know this whenever you're adding errors, because you know that whenever you add errors, the way you add them, you square little errors, and then eventually you take a square root. The error then grows like a number of terms you have included. And that's why you're dividing. In this case, parameter is time for the errors. And then there is some convention here, which is historical, having to do the dimension of the space in which the walk is taking place. So that's the simplest example of a transport coefficient. And then there is a whole theory, which I asked you to read, cumulants, which tells you how to compute other correlations, not just second-order correlation between the things. And this is now important in the settings where you have symmetry, isotropy in the space, so left and right is equally important. If you average just over the axis, you have to get zero by symmetry. But if you average over the squares, you're adding positive numbers, so you will get something that's non-zero. And we are actually guaranteed in set of dynamical problems that this has a limit and that this is well computable. And now the thing that you will not find elsewhere is that this has another expression, that this is a second derivative. And, you know, I might be missing some of the leading eigenvalue of the periodic operator. I mean, evolution operator, Perron-Frobenius operator, but now we call it evolution operator. But this is leading eigen of operator, which is the kind of operator we are used to, but it has an interesting twist. And before I get to this twist, let me just review the notation that we are using in this chapter. So inspiration comes from scattering in a hexagonal lattice. So that's a billiard problem, and it's naturally posed in terms of discrete time, number of bounces. But I think we should be able to use this also in fluid and cardiac dynamics, where you have continuous and not discrete symmetries. And the inspiration is that there is a big space which is filled out by our three-disk system, but then so this space I will call the state space here, so all possible places where you can be in that space, which is, you know, infinite two-dimensional plane. I'll call it M with a hat on it. So this is full state space. Then an obvious thing that we know from, you know, crystallography or condensed matter physics is that when you have a tiling of an infinite space, it's natural to look at elementary cell. And I'm not sure this is the best word, but that's what I call it. Where you think of this infinite space actually as unfolding of an elementary cell which is triply periodic. So the symmetry axis in this problem identified, and you make it triply periodic. And that state space, which is a compact state space, you know, this is infinite plane. This is some compact surface of which one edge is cut out, the disk is cut out, and you move on the complement, which is periodic in all the directions. I'll use no hat at all because that's where we'll do our work. So not, you know, to have fun in notation, a little bit painful. Now what we'd really like to do, and I've left it as a problem for you in one-dimensional case, we would actually like to live in the fundamental domain, which is this area here. So there is something that has an edge. You know, the symmetry axis is one edge, this symmetry axis is another edge, and then it ends here. So that's a fundamental domain. Now it's extremely easy to visualize this stuff, so I'll keep working on these discrete systems because you'll really understand everything. You know, this is the stuff here, the same thing. And this I'll call M tilde. But I won't come back to it very much. And the point is that if I know dynamics in this little space, I know exactly dynamics in the elementary cell because anything that's bouncing here has a relative in the big space, in the elementary cell. And if I know how I move in elementary cell, I actually know how I move in the big array because every time I cross this border, that corresponds to discrete symmetry that moves my cell. So, you know, if I'm a cowboy on a ICBM visiting current or former Soviet Union, whatever is your preference, then I will be moving through this regular lattice and I will always own a cell, but that cell will be related to original one by discrete translation, so by some integers. So this is kind of notation. And here is now the trick. We start at a point, so x without a hat means I live in this world. We start at x, and we move to time t in this world. So there is no hat. This is dynamics on a compact domain. It's something that's just moving around here. Time t later I'm someplace, and I'm at a point y someplace in this domain. So, I started here, and as you remember, the way we parameterize this is that we say we are someplace on a circle, so there's a length parameter or, parallel, and then we exit at some angle, and that angle is, from it we keep the parallel momentum, and for a billiard we always have a two-dimensional map of the phase space, and it's a discrete map because we go here, we re-enter, and the map is where do I land next time I hit this disk. So it's a discrete time dynamics in two-dimensional space. And now I do this in the elementary cell. So this y is where I land here. Now in the big world, what happens, I've actually gone someplace else. And I keep track of that, and here is the idea. I give this trajectory weight, which is beta times, and the miracle happens here, y x hat at time t minus where I started. So I started in the elementary cell, but I'll weigh my orbit by where I ended up in a big space. However, when I do integrations, what this evolution operator does is it takes some density in here and maps it into density on the elementary cell. And we allow it to do this because by symmetry of density, at least the eigenfunctions of the density, they should be same in all cells. So the miracle happens here. Our weight is we start at x, we end up y in the elementary cell. So in a little compact world, we go time t and we do the weight. Now I can write the same formula for the tilde world, for the fundamental domain. But then, for some reason which is not even clear to myself, I don't seem to be able to do this calculation. So, I'll leave it to it's a problem set. So what can I say? We're all busy people, and we did this and did something, and at that time we didn't know as much as we know today. So basically, for me, I would be very happy to revise formalism with the wisdom gained in intervening years. So this was discovered by Roberto Artuso in Italy, Gaspar and Ekman in Belgium, Denmark, etc., in collaboration some time ago. But this formulation of diffusion. So now whenever I have evolution operator, I now have a well-designed machinery to find its eigenvalues. And the simplest version of it is to say that the zeros of a function which depends on two parameters, c and beta in this case, and which miraculously can be written in terms of prime periodic orbits on this fundamental domain. Each one of them owning a weight which I call little trace. And this little trace is, for pedagogical reasons, and it's easiest to use the dynamical zeta function, this little trace is inversely proportional to stability of the periodic orbit. So this is product of expanding eigenvalues. Now I'll work out this in one dimension, so it'll be totally obvious. And then there's a weight, and for discrete processes, the weight of prime cycle of NP is the magic parameter zeta, which we use to construct generating functionals and find zeros. This parameter zeta, and its power is just counting the discrete period of a cycle. So how many bounces prime periodic orbit have? And then we put a weight, and this weight is always some funny parameter beta. Just like z, beta is also an auxiliary thing which we find very useful in calculations, but don't necessarily have a physical interpretation. As our integrated observable is d-dimensional vector, this is also a vector, there is a dot product. The weight is where I am in the big space after time np, after I've completed the prime orbit here, minus where I started, which was the starting point.